Good afternoon, everyone. Welcome to this webinar hosted by Rockflow Dynamics. It's Joanne here from the RFD Europe team. Thank you for joining us today. Today, we are bringing you another client-focused session from the tNavigator user community. We have a presentation and panelist discussion with Shell, showcasing recent work where automation and Python flexibility was used to enhance infill drilling projects. We will start with a presentation outlining the project from Bruno Rozenak, Senior Reservoir Engineer and Well Testing Expert. Bruno worked on this project with the Shell team in the Netherlands and has since relocated overseas, so was unable to join us for the webinar. However, he kindly offered to record the presentation in advance, which we will share today. For the second part of the webinar, we will have a panelist discussion and a chance to answer audience questions. We're pleased to welcome Bertrand Zwart and Gijs van Essen from the Shell Technology Centre in the Netherlands. Bertrand is a global water flood consultant, an integrated reservoir modelling and well reservoir facility management expert, and Gijs is a reservoir engineer in the well reservoir facility management team and an expert in assisted history matching and well location optimisation. As well as our special guests, we have my colleagues Alexandra Kidd and Georgie Colston from our tNavigator technical support teams in Aberdeen and Moscow, who worked closely with the team at Shell providing support throughout this project. So hopefully with this panel, we will be able to answer all of your questions today. Just a few things to mention before we proceed with the presentation. All attendees' mics have been automatically muted when you joined the webinar, so if you would like to submit a question to our panellists, please pop this into the chat box on your screen and we will answer as many as we can at the end. If we don't have time to address your question live, we will follow up with you by email in the coming days. This webinar is also being recorded and will be uploaded to our RFD YouTube channel later today. Please check our LinkedIn page for updates. Finally, if you have any follow-up questions, please reach out to asktnav@rfwm.com and we'll be happy to direct your question to the right person. Just before we begin, RFD would like to thank the team at Shell for sharing this project, and of course thank you to everyone who has tuned in to listen. I'll now start the presentation and we'll be back with you for the second part of the webinar.
This presentation is about well location optimization using tNav and its application on a large field. Well location optimization is a very important step to pick the right infill location and maximize the overall value of a field. That involves typically running many different well configuration and location that could be achieved with manual search, but would be extremely slow. So we use automation which needs to include some constraint to restrict the search space and avoid non-physical results. The optimization algorithm is used to help speed up the process and avoid local maximum. The specific challenges for this project was that there was an extremely large field with hundreds of wells, which meant very long simulation time. The wells that we were trying to optimize are those wells shown on the map, are highly deviated well and quite complex geometry. And lastly, the challenge that well location optimization is typically not a standard functionality in every software. So for the first challenge, the way we solved the large simulation time was to divide the field in different sectors and actually apply the well location optimization only on those sectors. So that was the sectors is quite easily set up in tNav, and the target was to have a simulation that will be between 10 and 30 minutes to be able to to run all those well location optimization. However, there's still some remaining challenges. It's not clear how you will pick up each sectors. You do have to calculate the fluxes between the sectors. So this is done when you create the sectors in tNav, but the fluxes are calculated between sectors for the base well location, and it is not updated every time you move the wells around. So that could be a problem. and maybe then it depends on your choice of sectors and making sure that the boundary of the sector is far enough from the well. And so finally, it's also required the final check with the proposed optimized location on the fulfill model to make sure that actually the proposed location do make an incremental. So this entire process took about 1 to 2 computational weeks to perform. The second challenge is around the complex well geometry. So the well is basically a highly deviated well that is being drilled from a well pad. So the way we parameterized it was the surface location, X surf and Y surf, which are typically fixed per well. The step out from that location, which has a maximum due to drilling constraints, the azimuths from the surface, then the azimuths in the subsurface. So this was fixed and basically followed the contour of the oil-water contact at the location, and the well length, which was varied. Another complexity is that we want to target specific layers. So when the topography of the layer varies a lot, that means that you need to follow this topography. Otherwise, you will actually get out of the target layer. So how did we actually implement that in tNav? To create those wells, you need to create a workflow. And you can access this workflow window by putting Alt W in tNav. Now this window shows you a panel on the left which have a lot of predefined functions that is already in tNav, and you can basically search with a search function. Then in the center panel, it's actually your workflow and the different block of your workflow. So you can see here I have the input variable plus 15 blocks. And the first block of this workflow is the input variable. So in here, you will put variable that you will want to vary later on when you do the optimization. So in this case, we had 2 wells, and I named the variable for the length, the azimuth, the surface, and the step out. So let's go into more detail for the actual workflow. So we saw that the first block was the input variable, and then you have different blocks which have the logo of Python, which are basically user code where that contains some Python. So I set up some local variable, import the libraries, and then define a bunch of functions which will be then executed later. So this specific function that I'm highlighting here is to create a horizon surface for each of the layer that will be perforated. Now, it is needed so that you can actually define the trajectory of your well. Now, what we use in there, apart from the standard Python, is functions that are predefined in tNav. So you have first to create the point sets of the layer and then create an horizon based on those point sets. The next function here that I would like to highlight is how to find the next point for your well in the next horizon. So what you see here on the graphic is let's say you already have created this point A and you want to find the next point B on the next layer. But you want this point to be at a specific length from the layer A. So to do that, you can write direct Python with the logic, and you can see I've put some example here. And what it uses actually predefined function in tNav, this thing here. So what it does is basically calls a specific horizon, or in our case, we will call the horizon I+1, and then get the value, so the Z value, at a specific X and Y location. So you can see how flexible that can be, right? Now, once you have this, you can repeat all of those functions to create the trajectory and create a given well. So that's what I did in this function. And finally, you will loop through all the wells and actually execute the code and create those well trajectories. So I gave you an example here of a well trajectory where you can see that the actual step out was 0. So basically the surface location is directly above the well. And then you can see how it follows the topology of those layers. Now, to create, so Python coding is not very complex, but to use the defined function from tNav, there is a very useful functionality. So say, for example, that you find something you want to do in those predefined functions. So example here, to create the top and bottom horizon. Well, you can actually click on that button. This will show the equivalent code in Python for that function. Now that code you can use in your own coding, which is what I did. Finally, you have to, so we have now the workflow that works, that creates a well based on few parameters. And now we want to use this workflow to do some optimization. So what we have done, we have parameterized the well. We've defined a workflow to actually create those well based on those parameters. And now we are going to use the automated history matching module to update the variable based on the on an objective function. And we will go through this loop in the hope to basically increase this this recovery. So to get to this assisted history matching, you will click on this magic button in tNav, and you will get, after a few clicks, to this window. And in this window, you can see that we have our variables, that the one that we want to vary, the length, the azimuth, and the step out, a minimum and maximum value. And here you can choose your optimization algorithm, so it will be Particleform optimization. And you also have to choose objective function, so which is in another window. In our case, we chose the maximum recovery for that sector. So we had to run this optimization for about 100 iterations, but I have an example here where I run it for 300 iterations for that well here, well 1. What you can see is that as the iteration goes on, the field, or I should say the sector ultimate recovery, goes up, which is what you want. You could also plot, so each of those dots corresponds to a different value of the step out, azimuth, and length, and you could plot those versus one of those variables. So in this case, I chose to plot it versus the azimuth, and what you can see there, it shows clearly that there's a region at 100 to 150 degrees from the surface location, which is a better location. So with this, you can visualize before the end of the optimization, which are the better location. In this case, it was between 100 and 150. So we basically run this optimization on each of those sectors. We got optimized well location, then we rerun the full field simulation with the new optimized location, and we compared the incremental between the initial and optimized location. And in our case, we found more than 50% increase in this in the incremental ultimate recovery. So it was definitely worth the exercise. And it took about 2 computational weeks to do the full thing, you know, with the sector optimization and the full field. So the conclusion is that we managed to complete the well location optimization, and we found more than 50% incremental compared to the original locations. And this was thanks to the tNav advanced functionalities. So the first one was the straightforward sectoring, which was needed in our case because the field was too large to perform optimization on the full field. The advanced workflow, so that combines tNav function and Python coding, and that allows a great deal of flexibility to deal with, you know, complex well geometries or any other things that you may want to do. And finally, we use the assisted history matching module to do production optimization, which was quite easy to set up. RFD support was very proactive during this process, and so that made my life easier, and that was quite efficient. And they're working right now on documenting further the tNav function and Python coding, which will be, I think, a useful complement, because this is quite a new functionality which didn't have that much documentation yet. And then the last point is that it did take still a week or two of computational time. So it's still very computationally expensive, but it is scalable. And when you set up a well location optimization, you should consider, the choice of a powerful workstation. Should you cut the field inflector or not? And tNav also has some cloud solution that allows you to run multiple runs simultaneously, which will speed up the entire process. So that concludes my presentation. Thank you.
Okay, that concludes the presentation part of the webinar. So now we'll move on to some discussion and Q&A. So I'd like to welcome Bertrick, Heis, Alex and Georgie to join us. And I'll let Alexandra lead the way. If you have any questions, as I said at the start, you can use the chat panel on the screen to submit those, and then we'll pick them up.
Good afternoon, everyone, and it's very nice to see the faces behind the study. So thank you all for joining today and for being ready to participate in this discussion today. There are quite a few questions that we received and they're already coming, and I will highlight that there's no way that we will answer all of them today, but there's also no way that we leave any question unanswered. So don't worry, we'll come back to you personally, privately, as you wish. We will be in touch. And there were some comments about the slides will be available, so I'll just cover and reiterate, as Joanne said, this video is recorded, so we'll have the video on, and that means that it's possible to see the presentation. If there's a need for slides to be separate, we can discuss that further, no problem. I'll start with the questions so we have all the time, and I first address an individual question to each of our panelists to capture the topic what was presented today. So first question I'll address to Bertrick, and it's about the well location optimization. And how do you think, how important is to consider geology whilst you're doing well location optimization?
Okay, thanks Alex for the question. Yeah, so we believe that WLO is particularly suited for addressing the heterogeneity and the variation in the geology in the models. So for example, if you have multiple models with different geological backgrounds, you can run the optimizer to take that into account. So you get actually a robust well location by uncertainty management at the same time. So the role of geology, of course, determines where you place the well. In other words, if you have defined your uncertainties, you can take that on board in the workflow and automate it. So in other words, you actually benefit from the speed up of the automation.
Okay, thank you very much. I want to continue a little bit on this topic, but I will pass the question to Heis. As I remember during the introduction, Joanne said that Heis is an expert in assisted history matching and location optimization as well. So from your experience, can you please share what are the challenges you encountered related to well location optimization, and how did you address them?
Yeah, thanks for the question, Alex. And I think it's a bit twofold. There's a technical angle to that question, right? And how do you actually implement the well location and the well in such a way in your model that you can start to investigate lots of different locations and different trajectories, while at the same time making sure it doesn't explode, right? So you have to be clever about how you parameterize that. And I think what Bruno showed in his presentation was a very nice example of that, being able to, with a limited number of parameters, making sure that we actually get a result out of that really works and could be drilled. I think that's always a bit of a challenge to keep that a bit in balance between the number of parameters and the time that we actually have to do a study like this. The other challenge that I often see, and Bertrick already mentioned that as well, is indeed the overall challenge that a model is just a model, right? And it's not reality. So we have to always be aware that what we're doing may be optimal for the model, but we have to realize that it's not reality. So we generally try to overcome that challenge by saying, okay, well, it's a first suggestion, but we need to do all the checks and balances to make sure that the well location that we end up with really is what we believe to be the best location. And using multiple geological realizations is one thing, but also integrating all the different disciplines to make sure that the well that we actually end up with in the end, when we actually start drilling it, delivers what we hope it delivers.
Perfect. Thank you very much. I'll cover one more topic that is related to that, but slightly separate, and I'll address this question to Georgie. There's quite a lot of similar questions asking, how important for engineers nowadays to know Python? What do you think, Georgie?
I know Python more or less well, I guess. I'm not a professional programmist, but I use it in my everyday life for solving some of my usual tasks. So my opinion that if you know Python, then it may simplify your everyday tasks and make your life more easier than you try to do it manually, especially if you try to manipulate with a big bunch of data, with a lot of files, with in our case with a project, a geology project, dynamic projects. So if you know it, it's good. You may make your life more easy. If you don't know it, it's not a problem right now because, as Bruno said, our support team is very proactive. So you may ask our team for help. We will be happy to help to you. And also, I may say that currently it's a lot of online courses for Python that it's very easy to learn, because I have never visited any courses, I mean offline courses, but Python I did it through books, through online courses, through forums and so on. It's very, very easy. If you want to start, it's a very low level for starting. If you compare it to, let's say, C++, it's very awful to start because you need to know very much about it, about computer technologies and so on. It's Python, it's another story, it's very easy to start. So if you know it, it may simplify your everyday task very well.
And if you don't, go and learn it.
Yes, it's maybe it's the best decision, but again, if you need any help, we're ready to help you. Because Bruno, okay, as I know, at the beginning of this project, he knows Python, but not very familiar with it. But at the end of the project, he created a lot of functions by himself without any support from our side.
So this is the course that you can take eventually. Thank you very much, Georgie. Yes, I can see some other question that is related to sector modeling and alternative options, which I find quite interesting. Would it be worth it to use restart on this process instead of implementing sectors? So instead of going through the sectors, to have the speed up or probably kind of more efficient approaches to use restarts. Who would like to take this one? Gijs, please.
I'll take it. Yeah, I think we did both here. So it's a good suggestion, but we used sectors indeed, but each of the sectors had a restart from the instant the well was supposed to come online, right? So we have all this history matching being done on the full field model. We take it up to forecast whenever the new well was supposed to be coming online. That's where we had to restart. And then we made sure that we had a similar restart for the sector model. So indeed, a good suggestion, but we did both. Yeah.
Perfect. Okay, so moving on, I have one more about uncertainty. So it says, thanks for the presentation. Did you consider uncertainty in the optimization process? Again, who would like to take this one?
I can quickly comment on this. So the workflow can be applied in combined with the uncertainty management workflow as well. In this study, as the computational horsepower we had limited us to work with a single realization, and what we typically do is after we have identified the optimal well trajectories, we are taking them into sort of the geology space with the geologists and check whether this is optimal, whether we have overlooked something. But we haven't checked it against sort of different porosity or permeability fields or different sort of reservoir architecture.
Yeah, there's several questions kind of along the similar lines, so we will add the details to each of them independently as well. I want to highlight a couple of nice comments coming through as well, saying excellent piece of work and excellent presentation. So wanted to share as well with you. Thank you for your comments. I was looking at this one question about considering multiple objectives. So it goes like this: can we include multiple objective functions, more than one, to be optimized, for example, maximum recovery and maximum cumulative production?
Yeah, I can take that. I think that's an excellent suggestion. I think that's often the case, right, where we have different objectives. For instance, we don't necessarily want to maximize recovery, but we also want to get there as fast as possible, right? So there's also a bit around acceleration there. The good thing, we didn't do it here because it was mostly about maximizing recovery, but indeed the option is there. I think the algorithm that Bruno in the end used to do the optimization has a multi-objective option to it. So you can identify or specify a number of objective functions, and it will indeed try to maximize all of them at the same time or at a specific way of weighting them. But yeah, it's a good thing that multi-objective option is there, because in reality, multiple objectives do play a role.
Mm-hmm. Kind of carry on this objectives, multiple objectives and optimization theme. There's a question about dangers. Any danger for local minima in the optimization process?
Yeah, I can take it, but I think it's definitely. I think it's the case with any optimization problem, especially the complex ones like these, that you end up in a local minimum or local optimum in this specific case. Yeah, the trick that we try to use is not to necessarily start at a specific starting point, but try different things, right? So that the way you get to your optimum, you allow for different routes, and sometimes you do find different optima. Luckily, also the optimizer that was used is a bit of a more global optimizer, in the sense that it's not easily will get stuck in a local optimum. Other optimizers are a bit more sensitive to that, but the risk is always there. I think we have to realize that.
Okay.
Yeah, I'll build on that, because the selection of the optimizer is an important step in this. But we do typically check 2 or more to make sure that it's working appropriately. So Particleform optimization was used in this study, and Gijs commented that worked out to be exploring, and we plot actually locations over time, so you see how the well is moving and you have a good feel. What we also do is we start analyzing the results, right? So we also go to understand, does it make sense? And in some of the cases, we realized it was moving the wells from one fault block to the other, and it typically makes sense because the faults are non-conductive, and you feel you've really reached a better optimum. So it was also making step changes and otherwise, right? Moving from one block to the other is a step change. It's not a continuous gradual function. So it worked pretty well.
Mm-hmm. Thank you. I think I will limit to 3 more questions. So there will be one more or less difficult, then the other one very simple, and then the final one very interesting. So let's go with that. The first one: do you apply clustering algorithm to divide the field in different sectors? So who would like to go?
So the short answer, I can start. The short answer is that we didn't do. So we upfront, depending on streamlines, that's what we used. We looked at where the biggest fluxes are, and you have to be careful not to cut long horizontal wells in between the various sectors. And there's some very simple rules of thumb to make sure that these sectors are a bit in equal size, but you minimize the fluxes across the boundaries. the sector modeling approach here does, in tNavigator has the option to taking into account and record all the fluxes at the boundaries. And if you rerun it, it will actually honor those. And indeed, if you change the well in location, it might change slightly, but we rerun it in a final sort of full field context. And you see that the error you make is relatively small compared to the larger bit. But we didn't do a cluster analysis on saying what part of the sector we should split into multiple sections.
Might be something interesting to try as well as an alternative approach to see.
I think so. Yeah.
Yeah. Now the other question that is probably very quick. Was the project a brown or a green field?
Yeah, very clearly brownfield. So we had about almost 50 years of history in this field before this new well. So it's clearly also infill wells we're talking about. But that's also part of the challenge in this field, right? And that's also where tNavigator came in, is that we had to do the history matching as well before we started with this project and use some of the history matching modules.
Mm-hmm. And to finish, I'll ask the last question, but this is definitely not all the questions that were received. So again, we'll be back with more comments. It goes like this. Why did you use tNav for the purpose when you have in-house application?
Frederick, you want to take this one?
Yeah, I can take that one. The answer is actually relatively straightforward. We're working on many assets. In some we're actually the operator. In some we're a partner, and we're delivering also services on the back. So in this case, the field already had a tNavigator model, and instead of rebuilding the model, we looked at the model. We did some updates, and tNavigator was available for us to do the analysis. I think for us, it was interesting to pick up the tNavigator and add our WLO technology on top of it. And I think that was the collaboration. And Georgie said, yes, Python was required. And Bruno spent a few good hours on scripting and having the interactions. But yeah, that was just the prime reason to pick up a tNavigator and enjoying the flexibility on the Python scripting for sure. So that made it possible to implement it.
Well, and also enjoy the beast, how you call the powerful workstation that you used for the project, yes?
Yeah, it was pretty fast.
Thank you very much. Unfortunately, we will wrap up on this, but all these great questions and comments are very highly appreciated. Thank you everyone to participate. I'll pass to Joanne to close.
Thank you, Alex. Yeah, Alex, as Alex said, thank you everyone for sending in so many interesting questions, and obviously thank you Bertrick and Heis and Georgie for joining us to answer them. So what we'll do is we'll pull all the questions together after the webinar. We'll have a look, and once we have them answered live, as I said earlier, we will get those answered and follow up with you in the coming days. So thank you very much to everyone for joining. Thank you to Bruno, who's not here, for recording the presentation. We look forward to seeing everyone at our next webinar. Thank you.
Thank you.
Thank you.
Bye.
Bye.
Goodbye.